So now that we know what Taylor series are, we're going to talk about how to tell whether they converge or not. Generally, if you can come up with a formula for what the derivative looks like, you can sort of just go about looking at the convergence using the ratio test or the root test like we have in the past. But if we don't know a formula for what the derivatives look like, it's sort of hard to get a grip on whether your Taylor series is going to converge or not, just by looking at the ratio of the consecutive derivatives, since we don't really have a formula for what that next derivative is going to look like. And that's how the Taylor series is generated for functions, is by taking derivatives. So that's not always going to work. It's for something like this, where we have sort of a formula for what the derivatives look like in the last video, in the last example, we can use the ratio test to show that this indeed converges for all values of x. But if we don't have that formula for the derivative, that's sort of not going to work anymore. So we have a way of looking at that, or a way of looking at the convergence of Taylor series that doesn't have to do with any of those root tests, or any of those tests that require us to have some formula for the sequence of coefficients. Taylor's theorem is basically just a broad generalization of the mean value theorem, where what the mean value theorem says is the function has to take on the average rate of change somewhere as its point of tangent, as a point of tangency. And so in this case, we're looking sort of at the average rate of change of the function, and then we're sort of looking at multiple derivatives here over that interval, and it's saying that at some point over that interval from a to b, there must be a point c somewhere in between, where the next derivative, where if we plug that into the next derivative, it'll sort of be the at leftover part. So this right here, all of this should be familiar as the nth Taylor polynomial with the point b plugged in. So that's sort of the endpoint. And then the idea is this leftover bit has to happen somewhere in the n plus first derivative. And that's Taylor's theorem, and we're going to sort of rewrite this so that it can be more useful. Right now we're using these endpoints of the interval a and b, and then finding a number c in between. But what we really want to do is we want to talk about it in terms of b not necessarily being a fixed endpoint of the interval, but being some arbitrary x value. And so that's where Taylor's formula comes from, is sort of rethinking that Taylor's theorem idea in terms of that, again, Taylor polynomial. So instead of just fixing the right endpoint to be b, the right endpoint of the value that we're plugging in is arbitrary number x in the interval. And then again, the nice thing about this is exactly p of x, or pn of x. Whoops, I didn't get all of the, just pn of x. And I missed the last term of pn of x. Here we go. This is pn of x, all of the terms up to the nth derivative, x minus a to the nth power. That's definition of the nth Taylor polynomial. And then there's some remainder term, some leftover portion. And what Taylor's formula tells us is that there's some c value that makes that remainder formula be the difference between the actual function and the nth Taylor polynomial. And that c value has to be somewhere between the center of your interval and whatever x value you're picking in your overall interval that you're looking at. And so what happens here is we have a way of now rewriting our formula as, or our function as, the nth Taylor polynomial plus some remainder term. So this is what we're going to call sort of the remainder, or if you want to think of it as the remainder or the error. But that's why it's the r. It's sort of that leftover stuff. And by Taylor's theorem, we're guaranteed that there's going to be a point C between a and x that gets this, that makes this true. And that's fantastic, because now what we can do is we can say, okay, as long as that remainder piece, as n gets larger and larger, tends to 0, then we have a way of saying that the polynomial, the Taylor polynomials, are converging to the function, right? The Taylor polynomials, the limit as n goes to infinity of the Taylor polynomials, will only actually converge to the function if this remainder part is going to 0. And so that's exactly what we're going to look for. We're going to say, okay, if the remaining piece, that remainder, that n plus first derivative, goes to 0 when n goes to infinity for every x value in the interval. So we need to show that that happens for any x value in the interval of concern. Then the Taylor series is going to converge to the function on that interval. And this is exactly what we wanted to know. We want to know, when does the Taylor series equal the function? Well, it's only going to converge to that function on an interval if the remainder term goes to 0 on that interval. And so we can see sort of how that would work in an example. So as an example, let's look at the Taylor series for e to the x. Show its Taylor series. Oops. Taylor series converges everywhere. So for all x values, let's use the Taylor series centered at 0, so make things easier on ourselves. And this is actually an example that I was talking about. You can actually come up with a formula for the derivatives, because in this case the derivatives are actually just 1. So being able to show this using the root test is possible. It's actually, so as an aside, we could do the root test e to the x equals the sum from k equals 0 to infinity, x to the k over k factorial, because all of the derivatives are the same, and plugging in 0 we get 1, so all the derivative coefficients are equal to 1. Let's use an n instead of a k. And then you can show, right, the limit as n goes to infinity of an plus 1 over an, right, that's going to converge to the absolute value of x. Or, no, it's not. It's going to converge to 0 for all x values. And you can show that using the root test, but we're not going to do that for this example, because generally you can't come up with a formula for the Taylor series that easily. Sometimes you can, but you need sort of a way to take care of this outside of those situations. So so this is one way to look at this particular problem, but isn't a way to look at every possible Taylor series convergence issue. So let's see what this looks like. Since the derivatives are equal to 1 for all, right, fn of 0 is equal to e to the 0, or 1, for all n, we get e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, all the way out to x to the n over n factorial. So this is my nth Taylor polynomial. And then there's this remainder piece, where that remainder piece is the next derivative with some point plugged in. And this is for some c between 0 and x. For any x value that we plug in, whatever our x value that we're plugging in, this will be equal to this, regardless of the x value. Actually, this isn't probably the best way to write this, because we're not sure whether x is positive or negative in this case. So for some c between 0 and x, okay. So what we need to figure out is the limit as n goes to infinity of these Rn's equal to 0. Is that limit equal to 0 for all values of x? For this instance, we're asked to show that it converges everywhere, so that for every value of x this is true. But generally, you just need to show that the limit is equal to 0 on the interval of convergence, the interval that we're considering. In this case, it's for all x values. And then we can look at it in two different ways, or we can break it up into two pieces. We can say, okay, well, when x is negative, the maximum value that gets attained here is 1, because e to the 0 is the largest value, since e to the negative power is a fraction, so it's always going to be smaller than 1. And you can actually just see that by looking at the graph, right? We know that e to the x is an increasing function, so if x is over here somewhere, then any value of c is going to be between 0 and 1, because that's what this value is. This is e to the 0, or 1. So the maximum value that gets attained on that interval is 1. So let's just say that it's less than that. So for x less than or equal to 0, we get to say that Rn of x is equal to e to the c n plus 1 factorial x to the n plus 1. That's going to be less than 1 over n plus 1 factorial x to the n plus 1, because e to the c for negative x is always going to be less than that maximum value on the right here. And then if we look at the same idea but with x on the right, if x is positive, right, whatever that c value is, since it's an increasing function, x is going to be the biggest that ever gets. So we can make the same argument for when x is greater than 0. But for now, let's just look at this. So now we're going to take the limit. So this limit, as n goes to infinity of Rn of x, it's going to have to be, since x is positive, or let's see, what are we? X is negative. Oh, by limit comparison or something like that, right? You can say that that limit is going to be equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, right? And that limit is 0. Or I guess more by the squeeze theorem is probably what's going on here, more than comparison. But so that limit's equal to 0. So for when x is less than 0, we see that it converges. And then for when x is greater than 0, we have sort of the same idea here, except now this is going to be bounded by e to the x over n plus 1 factorial x to the n plus 1. The e to the x is constant with respect to n, so it's actually not going to adjust the limit. The limit is still going to be 0. And since that limit is 0 for all values of x, regardless of what x we plug in, so the so Rn of x goes to 0 for all x, hence e to the x, or this summation, n equals 0 to infinity. Or they use k again. I don't know why they switch back and forth between n and k so much. But as k goes to infinity of x to the k over k factorial equals e to the x. That is to say that the series converges to e to the x for all values of x everywhere. So the way we looked at it was we looked at the limit of those remainders, right? The limit of this remainder was 0 when x was negative. The limit of the remainder was 0 when x was positive. So for any value of x, since the remainder goes to 0 in Taylor's formula, that means that the Taylor series must converge for every x value. So this is more sort of what you would have to do when you don't have some formula for the derivatives of your function. If you can come up with a formula for the derivatives of your function, you're welcome to use the ratio test or the root test. That will work just as well. But that won't always be the case. Won't always be easy to find a formula for the derivatives. what's interesting about this is now that we know what e to the x equals and that it converges for all values of x, we can actually redefine the number e to be the summation, right? The value of the summation 1 to the k. So if we replace x with 1, we just get 1 over k factorial. So 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. That series converges to the number e. And then more so from Taylor's formula, we can say, well, that's the nth Taylor polynomial plus the nth remainder with 1 plugged in. And that remainder piece can be bounded, and it can give us an estimate, an error estimate for how far off the nth Taylor polynomial is from the actual value. And that's sort of the next step, is if we can look at this Rn plus 1, our Rn of 1, which in this case was e to the c times 1 over n plus 1 factorial. Since e to the c, c is some number between 0 and 1, we know that this is bounded above by e to the 1. N plus 1 factorial, which we in turn can sort of even bound with a worse bound, but one that looks nicer. Right? We know that the error bound, the remainder, is smaller than 3 over n plus 1 factorial. So depending on how close my approximation needs to be, I can just take enough terms so that this remainder part is bounded above by some really small number, right? If I want this to be within 100th or within 1,000th or within 0.00001, I can know how many terms of the polynomial or of the Taylor's polynomial I need to do to get a close enough estimate for what I'm looking for. So we can use this to refine our estimates knowing how far off we might be, right? So this is error estimate. And so that's what we're going to do. We're going to say, okay, I want to get within 1/1000th, so that means I need to take the first 3, maybe, or how far does this have to go to be 1,000th? 6, 7 terms of the Taylor polynomial to get an estimate of e to the first power that's within a certain amount that we're looking for. So here's the remainder estimation theorem. It's similar to what you may have seen for the estimates for trapezoid rule and Simpson's rule, and that's because that's where this comes from. That's where the trapezoid and the Simpson's rule estimations came from. It comes from a Taylor's theorem remainder argument, saying that that remaining part of the estimate can't be any worse than this, since we're doing sort of geometric results using trapezoids and parabolas. there's a little more refinement that you can do in terms of, instead of the factorial, right, you get this number of rectangles to the nth power or whatever, but it's the same sort of argument. Right, we want to find a positive upper bound for the n plus first derivative on the interval that we're looking at. If we have that upper bound m, then we know that the remainder for our Taylor formula, right, the nth remainder, can't be any bigger than that bound on the next derivative times the x minus a to the n plus first, right? That's just the power, that's just the x term that goes with our n plus first term in our Taylor polynomial, and then that's over n plus 1 factorial, that's again just from our Taylor polynomial. So really all this theorem is saying is that what we're doing is we're taking this idea, we're taking Taylor's formula, Taylor's theorem and Taylor's formula, and saying, okay, if we put a bound on this derivative, then the remainder can't be any bigger than however big this could possibly get on the interval that we're looking at. So this isn't really an exciting theorem. It's really just a reimagining of Taylor's theorem and Taylor's formula in terms of the error estimations that we can make. So, and this extra part where it says if this inequality holds for every n and the other conditions of Taylor's theorem are satisfied for f, right? So if f is infinitely differentiable over a particular interval, right? Or at least I guess the first n derivatives exist on a closed interval, then if those things are satisfied, and we know that this bound is satisfied for every n value, then it's another way to say that the series converges, because if that's the case, then this limit, right, as n goes to infinity, is going to have to go to 0, because this factorial guy is going to take things over and in the limit. Since this is just bounded by a constant now, we're looking at a polynomial over a factorial, and the factorial is going to win every time in the limit, so this will go to 0. Right? The series converges since the limit as n goes to infinity of m x minus a to the n minus 1, or n plus 1 over n plus 1 factorial is equal to 0, which is the condition for Taylor series converging, is that remainder term has to go to 0 in the limit, and this gives us that if this inequality, if you can find a bound on that n plus first derivative. So as an example, show that sine x, or the Taylor series for sine x at x equals 0 converges everywhere for all x values. This one's a little easier, since if we're trying to do that, we can use the remainder estimate to show that, since if f of x is sine x, then the nth derivative is always less than or equal to 1. Since it's just going to bounce back and forth between sine and cosine, we know that the value of the derivative is always going to be within 1 of 0, because there's a max and a min for sine and cosine. They're always going to be between 1 and negative 1. And so since that's the case, so this is my m, then we know that the remainder part, which is the n plus first derivative, I guess I should say this is for any k, for all derivatives of sine. So the n plus first derivative with some value plugged in. I don't know what x value I'm plugging in. I don't care what x value I'm plugging in. X to the n plus first power. What I just found out is that's always bounded above by 1. The biggest this could ever possibly be is 1, because it's going to be some value plugged into the sine or plugged into the cosine, depending on what number derivative I'm at, whether I'm at an even or an odd number of derivative. I'm either going to be at sine or cosine, and it's always going to be bounded by 1, so I know this is at worst this. And then in the limit as n goes to infinity, this is going to be 0. So by the remainder estimation theorem, the Taylor series has to converge, because I showed that the remainder goes to 0 using that m upper bound was equal to 1 for all values of x. Right? This is true for any value of x. It doesn't matter what x value I plug in, this is going to go to 0. So technically, you didn't even need to show this part. This is sort of this is taken care of in the theorem. Once you say that I have an upper bound on that derivative for all values of x, you can say now, okay, I know that it converts. So by the remainder estimation theorem, the Taylor series converges everywhere. So the sum, or sine of x, is equal to the sum from k equals 0 to infinity of x, or negative 1 to the k times x to the 2k plus 1 over 2k plus 1 factorial, which we already looked at, right? All of those, it's just like when we took the derivatives for the cosine in that other video. All of the even terms disappear and we only get the odd terms left over, alternating in sign. So we have that the sine of x is equal to that by this remainder theorem. And then more than that, we can even say, if we look at a particular estimate of the sine using these terms, for instance, so sine of sine of x is equal to, or approximately equal to, x minus x cubed over 3 factorial, if we just look at the first two terms. Then we say the remaining part, right, that remaining piece, or let's write the remaining piece in, so plus Rn of x. Right, that remaining piece we know is, in absolute value, is less than this 1 over n plus 1 factorial x to the n plus 1. And so depending on what we want, how close we want our estimation to be, or I guess this should be 4, right? This is, I don't know why I did R4 is bounded by again, bounded by 1. We don't know exactly what the value of c is going to be, right? I guess I should write that in. We don't know exactly what the value of the fourth derivative with c plugged in. We don't know exactly what that value is. And since we don't know exactly what that value is, we're just going to bound it with 1, because it can't be any bigger than 1. But now what we know is that the remainder can't be any worse off than x to the 5th over 5 factorial. So if we want to estimate sine x with just the first two terms of its polynomial, its Taylor polynomial, we will always be within x to the 5th over 5 factorial, because that's the error estimate. And then if we want our estimate to be within 3 10,000ths, within 3 10,000ths, then we have to take x to the 5th over 5 factorial needs to be less than this number, which means that x to the 5th needs to be less than 5 factorial times this number, which means x has to be less than 5 factorial times that to the 1/5 power, which gives me that the absolute value of x is less than approximately So as long as I stay within about a half of 0, I can just use the first two terms of the Taylor polynomial and get an estimate for the sine of that value. And that's incredible, right? I mean, that's x minus x cubed over 6 is a much easier function to deal with than sine x, right? With sine x, you don't really even know where your calculator comes up with those ratio estimates and everything. This is one way to do it. As long as you stay within 1/2, you can use this easy polynomial. Plug in x equals 0.45. This will give you an estimate for the sine that's no worse than 3 10,000ths away from the actual value. And then obviously as you take more terms of the sine, the error estimate will go down, since this denominator, this 5 factorial, is going to get bigger, 7 factorial, 12 factorial, depending on how many terms you have. So that's sort of the nice thing about these error estimates and Taylor's theorem, and using Taylor polynomials to approximate weird functions.